Welcome to National 5 Physics again, scholars. This is section 3 of Unit 3, Part 4, Freefall and Terminal Velocity. We're going to begin with a very famous experiment conducted by the physicist Galileo on the Leaning Tower of Pisa in 1589. What Galileo did was he went to the top of the Leaning Tower of Pisa, which you can see in the picture, and he took with him two cannonballs, one of a very large mass and one of a much smaller mass. And he let them both go at exactly the same time, and he had a companion observer who was monitoring when they hit the ground. I'd like you now to pause the video and answer in your own head the question, which of the two cannonballs reaches the ground first? Well, the answer is that both cannonballs hit the ground at exactly the same time. And this puzzles a lot of people. Let's use our knowledge of physics to explain why this happens. So, what is going on? Well, firstly, each of the cannonballs that Galileo dropped is in what is said to be free fall. That means that the object is falling under gravity with no other applied forces artificially involved. So there are no wings, no rocket propulsion or anything like that. So the diagram shows you then the weight force of the body, W, which is mg, and it's pulling the body downwards. And at the moment, we're not including any air resistance. We will come to that shortly. Let's just ignore air resistance for the moment. And if we have the weight and the weight being the only force, then that's an unbalanced force. And so the body accelerates as shown in the diagram. So the body is falling freely under gravity and we observe it to accelerate. This means it must feel an unbalanced force. Now we know from Newton's second law that if a body feels an unbalanced force, Newton's second law must apply. So F must equal ma. But let's pause a second. What is our unbalanced force here? Well, we're neglecting air resistance, so there's only one force on the body, and that's its weight, mg. So the unbalanced force must be mg. So if the unbalanced force is ma, that's generally always the case, and in this particular instance, the unbalanced force is mg, then ma must equal mg. Now m here is the mass of the body, and it's the same on both sides of the equation, so it's going to cancel. And we end up with A equals g. Now what does that mean? It means that the acceleration of this body is equal to g, the gravitational acceleration, 9.8 meters seconds to the minus 2. But notice the mass of the body m has cancelled out of the equation. What does this tell us as physicists? It tells us that all freely falling bodies accelerate downwards under gravity, and on Earth that means at g of 9.8 meters seconds to the minus 2. And importantly, that is irrespective of mass. The mass does not matter. All objects accelerate under gravity at the same rate, no matter what their mass is. And that's why the large cannonball reached the ground at the same time as the small cannonball. Let's consider a very interesting example of free fall. In 2012, an Austrian daredevil called Felix Baumgartner went up in a balloon to 24 miles above the Earth's surface. Now that actually takes him to the edge of space, which is why he's wearing the space suit that you can you can see. And he leapt out of this balloon and he fell to earth. Well, let's have a look at the forces acting on him as he falls. Firstly, when Felix was outside the atmosphere, there was a little bit of atmosphere, but let's pretend there was none at all, then the only force on him was his weight. We are assuming no air resistance outside the atmosphere here, so no air resistance upwards, simply weight accelerating him downwards. Therefore, his motion is downwards, and we in fact know that that motion would be an acceleration if, and it's a big if at this point, if we neglect air resistance. So when he's outside the atmosphere, he accelerates downwards under gravity. The only unbalanced force on him is his weight. Now let's consider Felix inside the atmosphere. Well, his weight is still there, obviously. That's not gone anywhere. However, we now have air resistance or drag. That's going to affect his motion. His motion will still be downwards, but it will be affected by the size of that drag force. So, we're now going to imagine a body, a general body, in this case a ball, falling through the air as a free fall body. And we're going to introduce a new idea called terminal velocity. So let's imagine a ball falling from some height above the ground. There we go. And we're going to consider the forces on this body in 3 positions. Position number 1, just after it's been released. Position number 2, sometime in the middle of the flight. And position number 3, somewhere towards the end of the flight before it lands. So there are positions 1, 2, and 3. I'm now going to draw a force diagram for the ball at each of these 3 positions. Now the 3 positions are vertical positions, high, medium, and then low, but I'm drawing them across the page left to right for clarity. So let's focus on position number 1, just after the ball's released. Well, it does have a little bit of drag force there, not very much because it's not had much time to build up speed. So a small amount of drag, and it of course has weight. And you'll find that typically, depending on the size of the ball, but typically the weight will be a lot bigger than the drag at this point. So the ball's going to accelerate an unbalanced force downwards. At position 2, what you notice now is the body's been falling for longer, and so the drag force is increased. Experiments show that the faster you go through air, the bigger the drag force. And you may have experienced this when cycling. So the drag force has got bigger, but the weight remains the same size. Obviously, it doesn't change. And then finally in position 3, just before we hit the ground, well, we've been falling for quite a while now, and the drag force is really built up because the speed has built up. So big speed, big drag force. The weight, of course, remains the same. Now the question is, how big can the drag force get? Well, we find in practice that the drag force can never be any bigger than the weight itself. If you think about it, it must be impossible for the drag force to become bigger than the weight, because if it did, then the ball would decelerate on the way down of its own accord. And it seems ridiculous that a falling body would just naturally decelerate all by itself. So the biggest the drag force can get is to equal the weight, i.e. to balance the weight. So we end up then with balanced forces, and in this case the drag force equals the weight. Balanced forces, as you know from Newton's first law, results in a constant velocity. And this is a very special constant velocity called the terminal velocity, v subscript t. It's called terminal because that's what the velocity ends up at when any object falls through air. If we plot a graph of velocity downwards against time, we typically get a graph shaped like this. And if you look at position 1's force diagram, it corresponds to the very beginning of the graph. You'll notice the line is quite steep, so the velocity is increasing quite a lot per second. So quite a big acceleration at position 1. Midway through the motion, or a little bit further on perhaps in position 2, you can see the body is still accelerating. There is still a little bit of slope upwards on the graph, but it's much less. So there's an acceleration at position 2, but a much smaller acceleration than at position 1. And then by position 3, the line has stopped sloping altogether and it's become horizontal, i.e. the velocity has become constant. And when that line flattens and becomes constant, we have the terminal velocity. And that's the speed the object would end up going at, and it would never get any faster than that terminal velocity. Just considering terminal velocity for a few moments, I mentioned earlier that as the body gets faster, the air resistance or drag gets bigger. I've shown you how it does that on a graph. You don't need to know about this graph for the National 5 course, but I find pupils tell me anyway that they find it useful to have seen it. So it just shows you that as the speed of the body falling gets bigger, the drag force really rises quite rapidly as speed. So what you do need to know is the greater the speed of a body, the greater the drag force from the air opposing its motion. And a little summary then of the body in free fall just shows you that at the instant of release there's pretty much zero drag or very small drag. Later on, when it's speeded up a bit, you've got some drag, and then eventually all falling bodies always end up with a drag force that equals their weight if they're allowed to fall for long enough so that their speed is big enough for a big enough drag to balance the weight. And we end this section with a very famous experiment called the Guinea and feather experiment. The Guinea and feather experiment, which I will show you in a separate video clip, basically involves taking a glass tube as shown in the diagram. It's maybe about 5 or 6 centimeters in diameter, and inside it you put a small feather and traditionally a guinea. Now a guinea was a coin, so imagine a pound coin. And you connect up the tube to a vacuum pump so that you can suck the air out of the tube if required. Now with air in the tube, first of all, what you do is you let the guinea and the feather settle down at the bottom, and then you very quickly turn it upside down and you watch what happens to the guinea and the feather. Now when there's air in the tube, what you find is that the guinea coin falls quite quickly, but the feather, trapping the air and being very light, just floats down very gently. So the guinea reaches the bottom first. Then what you do is you evacuate all the air out of the tube, and then you repeat the experiment. You let the guinea and the feather settle at the bottom, then you quickly turn it upside down, and what you find quite astonishingly is that the guinea and the feather both fall at exactly the same rate. Now many people think that when the air is in the tube, the reason the feather reaches the bottom after the guinea is because the guinea is heavier, but that's not the case, as you saw earlier. It's actually to do with air resistance, and when you remove the air so that it's not a feature, you find the feather and the guinea reach the bottom at the same time. Here's a little bit of analysis then as to what's actually going on, and this will make more sense if you see the video of the experiment, which I'll post separately. Well, firstly, with air in the tube, let's consider the guinea and the feather and the forces on them. Well, the guinea will have a force, its weight, mg, the small g is for guinea, and it experiences a little bit of drag. Now the important thing here is, because the guinea is made of metal and it's quite dense, it's got quite a big weight, But because it's not that big, it doesn't really have much drag. So small drag force and quite big weight force. The weight force is clearly bigger than the drag here, so there will indeed be an acceleration downwards, which will be close to 9.8 meters seconds to the minus 2. If we now consider the feather, well, the feather is very light, so it does have a weight, but it's quite a small weight force. That's the green arrow shown. It also experiences drag. Now its drag force is broadly similar to the drag force of the Guinea because they're about the same size. The big difference is the tiny drag force that the feather feels is about the same as its tiny weight, so its forces balance. And so when there's air in the tube, the feather moves at uniform velocity, just floats down gently, because its weight is balanced by the drag. The Guinea, on the other hand, has quite a small drag force but a much bigger weight, so it accelerates downwards and wins the race to the bottom, so to speak. So that explains why the Guinea hits the ground first. When you take the air out of the tube, well, there can be no drag now, so the Guinea has its weight force and the feather has its weight force. No air resistance. All bodies accelerate uniformly under gravity if there's no air resistance. So they both accelerate at g, technically 9.8, but approximately 10 meters seconds to the minus 2. And there we are, the Guinea and feather experiment. Well, scholars, that brings us to the end of National 5 Physics, Unit 3, Section 3, Part 4. I hope you enjoyed it.